Hello, good morning, good evening, good afternoon, everybody, wherever you might be. Hola, muchachos. Today we have a speaker from Mexico, ELMAR WAGNER, and he will tell us about the Schochet spectral sequence for finite quantum CW complexes. ELMAR, the floor is yours, the Zoom is yours. Take it away.
Thank you. It's an honor to be able to present this talk in the seminar and with these experts in the audience. But I don't want to raise the expectations too high. So first thing is, here in the title is finite. So we will only see finite spectral sequences, which are not so complicated. And one of the reasons I gave this, well, there are two reasons why I wanted to give this talk in the seminar. One is that in summer I had this, in Simon's lecture, I didn't finish my plan. I wanted to talk in the science lecture course, which was for students, about spectral sequences. These are nice examples and are easy to understand because they're finite, but there were so many questions I didn't get to discuss the differentials of the spectral sequence. And the second reason, which is even more important, is this is a joint project with Alicia. Alicia is my PhD student, so I gave him this as a topic for his PhD thesis to find the comparison theorem. So we have classical CB complexes, then we have an idea how to define quantum CB complexes. You will see it. I will do it very slowly. So once we define what is a ball, what is the inside, what is the boundary, we require that the topological invariants in skulls of K0 are the same. Then we know how to clue. So formally, we can do the same thing as in the classical case, but we would like to have some theorem that tells us we don't change the topology. We have the same K groups. And the idea was, or the hope was, to trace back these elements in K0 from the spectral sequence. And we have a nice description of the first differential, as usual. And as usual, what happens for spectral sequences is it's difficult to trace these higher differentials on elements. So we know it exists, we know how we describe them, but we have no explicit description. And that makes it difficult to compare on the nose the K theory of the quantum CB complex with classical counterpart. So let's start. And then I start very slowly. So we want to study quantum CB complexes. I have no idea how to deform a single point. I'm not interested. So we start with a set of points classically. I'm not interested in defining deforming intervals. So our X1, our first skeleton, will be obtained by gluing intervals to a set of points. So we write it as a Bashout diagram. We have some disjunction from intervals. So the boundaries are just 2 points, -1, 1, which we have an inclusion. And there's a map that tells us to which points we glue the ends of the intervals. And that is this gamma 1. Write a Bashout diagram, which says, so going to the left, it should be the same going to the right. And we get a skeleton of dimension 1. And from here is an example, 3 points, some arcs, glued to 3 points. So that's classically. So I don't care that this first one is still classical. And then we go higher, and here are some disks. We have some nice idea about how to deform disks. So let's go include disks to some one skeleton. So we take a disjoint union of disks. We include the boundaries, and gamma 2 tells us how to glue the boundaries on the skeleton, and we write again as a Bashout diagram. So both ways should be the same, should become commutative. And here's an example. So we have this, the black one is the X1 skeleton, and I choose to glue 2 disks on this circle. That's it. Now that can easily be deformed disks. So
Elmar, did you use the magic word push out?
push out, yeah, it's written somewhere. So
I
at
don't see.
least
Yes, it's written push on that. Yes, thank you.
that's good. Yeah, uh, because we want the push out diagram. What I want to do is obviously I want to apply the C functor and then reverse it to a pullback diagram. So we have zero skeleton, we have one skeleton. It's classical, it doesn't matter, but now we can go by induction. So if you have an xn skeleton, we take n disjoint union of n plus 1 balls. Here we insert the boundary, and again, everything non-trivial is this gamma, which tells us how to close boundaries on an xn skeleton. We consider the push out diagram and get the xn plus 1 skeleton. So it's fine that at one step we will stop. So what we want to do the same thing for C star algebra. So to just apply the C star function. These are above our push out diagrams, so we get pullback diagrams. We start, as I say, classically with some set of points. Once we have an xn, we take the C star algebra of xn, we take the C star algebras of the balls. Now these elements, we inserted the boundary in the balls. Now it comes the restriction. Functions are just restricted to the boundary. And this non-trivial cluing, which was hidden in this gamma n here, so we take the pullback, that says how we clue, it still has information how we clue these boundaries on the xn skeleton. Now this is a push-out diagram. Here's just the projections on the left part, this is on the right part. And these functions, cxn plus 1, these are pairs of functions such that going on the left or going on the right gives the same element. So that's pretty much known. So
Sorry, Elmar, may I ask you a completely dummy question, please? Why is this gamma n plus 1 unique?
No, I'm not saying it's unique. No, this is just, I wanted to put this exclamation mark. I want to say, I want to keep track of this gamma. I wanted you to notice anything non-trivial is in this gamma. That's why I put it to make it. I made it green. Okay. Yeah, I made it green. I put an exclamation mark just to say what's happening on the right side. That's pretty standard. Anything non-trivial is in this cluing map, and so hold off. I will keep it green so you remember that's where the non-triviality is, and that will determine in the spectral sequence our first differential.
Okay.
So from now it's okay if you notice that's a special part of the cluing. So it's non-trivial. So again, now
is that trivial things are blue and important things are green.
Yeah. The part that tells me about gluing, if it's consistent, I always made it green. That's where the information sits. The other thing that don't carry much information.
Okay.
So that's classically. Okay, above is I repeat it classically just for xn. Now I want to have a quantum. So we start with x0, we take points. I don't have an idea why I should form points. Then I have an x0, and then I can go back by induction. So what I need is some concept of non-commutative balls, closed balls, a map that can be interpreted as a restriction to the boundary. And then it doesn't matter whatever I map, I consider this field change to tau n. That tells me something about the cluing. So it can be any map, and which corresponds to the cluing. And if I find one, okay, I'm happy. But when the problem arises if I want to say, oh, I'm constructing a sphere, I'm constructing a complex projective space, then these should have some similarities to the classical one. Right? So the information isn't there. So if I want to compare some quantum construction to a classical one, so there should be some way to compare this pullback gamma and star with the star. But the first thing we need is these balls and boundary spheres.
And
So
here
to
you
be
mean, here you mean possibly non-commutative, but surely unital.
Yeah. Yeah, okay. A comma might have done it.
Yeah. But unitality.
Okay. So yeah, the concept is clear. I can write push-out diagrams, non-commutative push-out diagrams. So, and it might look like this. So that, well, what can I do? I can do by induction, write push-out diagrams, push-out diagrams, push-out diagrams, and I can generate non-commutative histology paths. But I wanted to have analogs of classical TW complexes. So these algebras, which I call quantum balls, should resemble something which is classical ball. These spheres, boundary spheres, should resemble a classical sphere. Otherwise, it doesn't make sense to call it a CW complex. And I want to compare, where is this exclamation mark? I want to compare it with classical construction. So it's not enough just to take the same numbers of balls. This tau n should have the information which says classical quantum has some relation. So since these are topological objects, I would like to conserve some topological invariance. And since for histology paths, K-theory is some sort of a topological invariance that doesn't care about commutative histology paths or non-commutative histology paths, it goes just the same way. So this is a preferred choice of a homology theory is K-theory, taking K-theory and trying to construct quantum CW complexes that conserve the invariance, the K-theoretical invariance.
So Elmar, would you agree that K-theory is the most ethical answer to your moral questions?
Yeah, that's true. Very good say. Well, no, I don't want to lose time with it. Yeah, but it's a very good answer. So it's the best I can. Well, the answer is that's the best I came up with. That's a better answer. So someone might have better answers. So we need balls. So what non-commutative histology paths are candidates for ball? So ball comes with an exact sequence. I have these zero functions on the open ball inside as a closed ideal, and if I take the quotient, that corresponds to the restriction of the boundary. We know the K-theory. It's rather simple, but not trivial. So for the even dimensional balls, we have some non-trivial generator. So the closed balls are constructible. So that should be the same case. K-theory should be the same as the K-theory of a point, so a set of one. The boundary of an even ball is an odd sphere. So K-theory is trivial. Then we go on. K1 of the even dimension is trivial. K1 of the closed ball, which is constructible, is trivial. And here comes some non-trivial generator. So the K1 of the boundary is an odd sphere. So we have one non-trivial generator. And then we go to look at the odd balls. So K0 now is trivial, same closed ball is K0 of a point, and the boundary of an odd ball is an even sphere. So we have one trivial generator that comes from the one, but there's this spot type generator, one non-trivial. And in the case of a classical ball, well, these are actually more or less the same generators. So these spot type generators, which I find on an open ball, if I compactify it by 1 point, I can take basically the same generator. Now the K1 of the inside of the ball, of an odd-dimensional ball, if I compactify, get an odd-dimensional sphere. It has an unique, well, it's set, it has a generator which can be compared to this one on the boundary. So these are essentially the same generators. And then it goes on, K1 of the closed ball is 0, and K1 of the boundary is now an even sphere, 0. So that's what we want to do. Well, that's the minimum requirement for quantum balls. So to have some sort of quantum ball, we want to have a system algebra, which represents the closed ball. Some closed ideal, which we consider as functions on the open ball, the zero functions, and the quotient we interpret as the restriction on the boundary. That's it. So we need actually one system algebra and one closed ideal. But you want to have the same K-theory invariance. Now that means, so what we require is K0 from the open ball, C0 of the open ball. Yeah, now quantum should be generated should be Z with a distinguished generator. That it doesn't matter too much, but I put here a name for the generator because if we look now at the K0 of the boundary of an odd sphere, so we get an odd ball that gives an even sphere. So these generators don't have to have any relation. These are different algebras. So I don't care about this relation we had in the classical, just Z. So this is Z. This is one copy of Z. Then closed ball trivial, just one. Here again, closed. So it's an K0 of an even dimensional, no, odd dimensional quantum sphere. It's trivial. K1 of an even space, even disk, or even ball 0. Here we get this K1 of an odd boundary sphere. It's set, but our generator doesn't have to have any relation with the K1 of the inside of an odd ball. So if you look at just at the blue ball thing, so it sets, it repeats the classical situation. So here it's a bit smaller, has the classical situation. If you look at the quantum situation, it should be the same. So that's my first requirement, to call a ball, the sphere, and the inside. Now, so whatever you find, it's admissible. And there's one easy solution, just to present an example. And that starts with our famous quantum disk. So as I said, the sphere skeletons and points of the one skeleton, I take just the classical part. I don't form the functions on an interval. But we have a nice notion of a quantum disk or a quantum two-ball, closed quantum two-ball as a Doppler's algebra. It has an unique closed two-sided ideal to compact operators. And the nice thing is, if I take the quotient of the Doppler's algebra by its inside, the compact, I get a classical, there's functions on a classical circle. So that circle, which is a one-dimensional skeleton, It's classically, so it fits very well in taking the first one classically, and it starts to be non-commutative by taking here these. So this is non-commutative. We have a non-commutative inside, just a compact, and one scalene remains commutative. So it works perfect. So for two-dimensional CV complexes, we can construct any of them exactly as in the classical case. We can have a look at the K-theory, of course, inside are the compacts, set. So it's an even ball. The inside is fed, generated by some sort of a bot projection, exactly as in the classical case. K1 of the compact is 0, as we had in the previous case. While the doublets algebra is a closed ball, has triple K theory, is just Z1, and K1 is 0, as it should be. And if you take the quotient, the boundary circle, of course, that's the classical circle, has the same K theory as one circle as we had before. So from these, this is enough. So this is just an example. You can take any, and I had the idea for Ale, so we can take any C-stalker extension when if you know what is a ball, and if you know what is boundary, we just can study the C-stalker extension and work with those. But to have an easy example which works, which gives nice results, we look at the classical balls, we write as Cartesian product of two balls. So we can take as a C-star cheaper the tensor product of the C-star cheapers of the two balls, and that we consider as functions on a 2K ball. These are the even cases. The inside, of course, is just taking the tensor product of the C0 functions. And the boundary is taking the quotient. So that's taking this quotient is analog to taking the restriction to the boundary. Now, the quantum analogs is since we have the non-commutative do this, we have an easy way to get an analog. We take as a 2K, the even-dimensional balls, just the tensor product of K doublets algebras. It's nuclear, so there's no problem with the tensor product. And the inside is the tensor product of the compacts. Of course, it's just one copy of compacts. So if we take the boundaries, then taking the tensor product of the doublet algebras, dividing out the compacts, and that's our restriction to the boundary. So in this way, of course, we consider some quantum sphere by taking the inside, compactifying by 1 point. So the inside is compact so the compacts compactified by 1 point. It's interesting to see that all inner points, so the insides of all balls are compact. It doesn't depend on the dimension. Each C0 of P to K is just compact. So the compacts have any odd dimensions. It's a fuzzy point of any odd dimension, which is a bit strange, but it works. So if you want to have odd balls and even spheres, we just...
If you can go back to the previous slide just for a second.
Yeah.
Yeah, so these are exactly our multi-Poolbeck quantum spheres from our paper with Richard Nest and a bunch of other people. Please allow me this comment because there's some, I believe, interesting non-commutative topology behind. So there, in particular, these C-star algebra, these balls, the spheres, the boundary is of course the sphere. These are not really spheres, they're like multi-discs. Of course, a multi-disc is topologically a sphere, and its boundary is topologically a ball, and its boundary is topologically a sphere, but these are sort of very non-round spheres, if you think about it. But we obtained them by a bottom-up construction. So with Bartek Zieliński and Atabek Kaigun, we decided to create, multi-pullback quantum complex projective spaces that would have a particular feature that they would admit a covering that would generate a free distributive lattice. This is one of the beauties of a canonical open covering of projective spaces of any field, that they are a model for a free distributive lattice, which is very important in the lattice field. And we wanted to have a deformation which would preserve this particular property. And we succeeded with some very complicated, transition functions to really mimic the classical case using exactly these multi-disks. And then we are wondering, but what is the sphere from which these projective spaces come as fixed point sisters about? And then we discovered that these are exactly the spheres that you wrote down here. And then we discovered that there are higher rank graph sister algebras. And to make things more complicated, Richard Ness twisted them by theta. So we have a theta version of all. So
Thank you for the comment.
Yeah.
Yeah, I'm grateful for the comment because it's exactly my philosophy. You can do anything that works as long as you observe the case theory.
Yeah.
You can construct. I gave it to Ali to find the quantum projective spaces with this, and I think he didn't succeed yet. But I'm sure we can construct some sort of CV-W complex of the quantum projective spaces, and then it would be interesting to compare. Yeah, and even in the remark that this doesn't look like a round sphere. That's exactly what I say. It's what I permit. I permit everything as long as I can call it a sphere if it has a topological invariance as I like.
Exactly. Yeah, that's our philosophy as well.
Exactly.
And will you come to Von-Szymanski balls at a certain moment or not?
I took an easy example. The quantum complex. So complex projective spaces, because it has for the spectral sequence, it has nice property. You write down the E1 page, then you read off the E2, and then it's stationary. It's a nice example where spectral sequence on the nose gives you the result. So that's the only example. I know it's very trivial, but I choose this trivial example to show you that in some cases, the spectral sequences are a very beautiful, powerful tool to read off the case theory.
Okay. So, but you.
So I'm sorry for
not as an example, right?
Excuse me?
Okay. And by the way, look, it was sufficient that I mentioned the name Richard Ness, and now he appears.
Okay, very good. Welcome. So, yeah, what spheres, you see, I'm not very creative in defining what spheres. I just take one more dimension, an interval, and that's classically. So I tensor it with the classical C1 to get odd dimensional boards. But as I said, it works. And well, if we get this three protected spaces, then maybe we can see that's not so trivial as it looks. But then the inside is just they're taking the inside of the walls times C0 of the interval. And if you take look at the quantum analogs, well, that's just doublet with C of the often closed interval. Nothing special that happens. The inside is now the suspension of the compacts. Yeah, this tensor product of compacts is just one copy of compact, but we now have suspension. Suspension allows us to construct, if we start with a sphere and then we take suspension, it's another way to construct quantum spheres, but it's very commutative construction. So we take the quotient, you have the restriction to the boundaries, just taking the quotient. And you get the spheres now by taking the suspension of the compact operator and compact define. It's another sphere, but it's not exactly the sphere we have here. Yeah, these are different spheres. We have different generators. And we have a look at the K group. So I wanted to make sure that these balls and spheres and insides have the same K groups. So the doublet algebra, here we have nuclear system algebra, and we have any of these. We have seen that these K groups that we have never seen torsion in all these K groups. So we can take Kunnert theorem and on the nose, so we get K0 of the doublet algebra. Since any tensor factors trivial, we get the trivial K group Z1, exactly as in the classical case. So same for K1. If you take Kunnert, you have always a 0. So it's 0, exactly as in the classical case. And the inside, the compacts, we don't need any Kunnert theorem. Compacts just give one copy of Z. We take one-dimensional projection that generates the K0 group of the compact. But it happens that it's the same for all even-dimensional disks or balls, open balls. So K1 becomes 0 for the compact, as in the classical case. Oh, is it on the even case? Yeah, K0. The boundary. If you have on the boundary, you have 1, and then we have K1 of the inside, but that's 0. So what I'm doing here? Okay, well, the result is should be clear. I think I confused it here. So K1 of the even sphere, well, if here K1, we cannot take Kunnert theorem, but we can take the 6-term sequence, and then we get it's isomorphic to the K0 of the inside. So we have one generator and it's one copy of Z. It works. So in the odd case, I added an interval. So if I have the open interval, it's just a suspension. K0 of the closed balls gives nothing new. It's trivial in both cases. K0 of the inside. Now, here it's a suspension of the compact. K1 of the compact is 0. So we get really 0, as in the case of the classical open balls. K1 now of the inside of the open balls is the suspension of the compact. So it's isomorphic to K0 of the compact. We get one element which generates it. So it's one copy of Z, exactly as in the classical case. What else? So K0 of the boundaries. So that's, well, one is now I remember what I'm doing here. It's one of the Z is clear, and the K1 that comes from the 6-term exact sequence. If I go down to 6-term sequence, I get some isomorphism with K1. So that comes from the generator of K1 of these balls, open balls, produces in the connecting homomorphism that one. So the connecting homomorphism of K1 produces these projections. That's what I wanted to do. That I mean, this is putting in K1. So the rest, K0 is classically, K1 is 0 classically. So our tensor products of doublets and with an interval works as examples for balls, spheres, and the inside. And here's my example, the famous CBN, which is easy to construct. And it's a nice example for showing that we don't alter anything. So it's slightly trivial. So we start with X. So 0 skeleton is just the point. And just the point I can look at as a classical CB0. Now it's
so why is 1Q black in your slide?
Well, here that's because that's in a case in one skeleton there's no
yes,
quantum.
I got it. Yes, because it's really a point. Okay. Okay.
It's any one skeleton I take classically. So Q doesn't
Yeah.
mean anything.
I've
Now
got
this Q, yes, this Q doesn't mean, but that should be blue. This means
Yes.
something. Now I can start with something honestly non-commutative.
yeah.
So I flew a two-pole on a CP0. Well, that's the general construction is I flew a pole and 2k pole to 2k minus 1 projective space. So here the starting of an inductive process. So the CP0Q was just a single point, and I take this two pole as a Duplex algebra, and I have to glue these things. Now here, since it's a C, there's only one more morphism. I can take this number alpha to alpha times 1. And 1 goes to 1 is unit homomorphism, and I define the CP1 as a pullback of these two morphisms. So what does it mean? Any element, so an element is, so in pair, the number plus and Duplex operator is in CP1 is the simple map on the Duplex operator gives a multiple of the unit. So that means we get all the compact operators, which gives 0, and the unit. So it's just the compactification of the compacts. That's the standard Bottle sphere, and the standard Bottle sphere is known to be it's generally considered as a CP1Q. So that's fine. We just reconstructed something known as CP1Q, and then we go by induction. Now we have some CP1, and we want to have a CP2 and higher. So it's maybe what's important here is, since here LC, I just inject, this is an injection, and this is the pullback diagram. So I get an injection of my CP1 sits inside the Duplex algebra. But that is a condition which I will need for my induction process. So CP1 sits in the ball, in CP1 in the two ball, and now I go with an induction process where the CPK sits inside the 2K ball quantum. So that's my condition for the induction process. Now I define CPK plus 1 by taking CPK and writing down the pullback diagram with one single 2K plus 1 ball. So the ball with the right dimension. Now I state by induction, I know that CPK2 fits in the tensor product of K times Duplex algebra. So this mapping, I take the element from the CPK and map it in this element Z and Z times 1. So it always land on the boundary, because this one is never leads to a compact operator. So it survives. This mapping survives under the quotient by its compact. So it's an injection. So since this is an injection, my pullback diagram will give me an injection in my 2K plus 1 ball. So here it's just it's restriction to the boundary, means quotient with the compacts. This injection leads to this injection. So my CPK plus 1 sits inside K plus 1 copies of the Duplex algebra. And then I go on higher. So I have only even dimensional skeletons. The odd ones, it's like the one lower. And by induction, I can define any CPN Q, always inside the tensor product of Duplex algebras. So that's one example that works very well and it's easy to understand. And this one, we will see the spectral sequence, which also knows gives the result of the K-theory, which is very easy, but it's a nice application.
Sorry,
So
could you
here's
go
a
back
model
to the
question.
previous slide?
Yeah.
Okay. But is it no previous slide? Wait a second. Where you have this induction definition of CPQ? Oh yeah, this one. Sorry.
Assumption here.
Yeah.
The assumption was.
Yeah. Okay. So I understand that these C-star algebras standing for these quantum complex projective spaces, they are isomorphic with the usual Waxman-Seubel C-star.
Yeah.
Okay.
Yeah, that's true.
So in this case, I have a question to my co-authors, Tomek and Francesco. I have a vague feeling that all of this is in our paper from several years.
Yes, it is. It is.
All
Right.
of this. Yeah. Okay.
Yeah. That's your construction.
Yeah.
I
Okay,
choose this example not because it's new. I choose this example because it's easy.
Yeah.
Yeah,
Double
it's-
checking. Yeah. Thank you.
But I even was interested in an easy example because we come back to our moral questions. The only thing which I did is, while I made an induction process
Mhm.
similar to the classical one, and I include always one ball on one ball of a dimension plus 2, do a projective space. That's the only thing in the moment which motivates we have a complex projective space. Yeah? But does it really conserve the topological invariance? And that's again where I chose my green color. So the reason to call it honestly a quantum projective space should be in the map, in the excluding map. The excluding map should have the information. It's indeed a quantum complex space. So we can have a look if we can compare it, this map, from in the quantum case to the classical case. Here it's still simple, because if you look at the boundary, so we have the boundary spheres of even dimension gives odd dimensional spheres. So we have K0 is set, but no, K0 is trivial, but K1 is non-trivial. Now, if we look at the classical case, K1 is always trivial. So classical, we have only non-trivial elements in K0. If you look now at this induced map, so dow to K plus 1 tells me how I clue. My moral question is it should clue in such a way that we don't change our topological invariance. But since so K0 goes to K0, now this one, so it's an odd sphere, has only trivial K element, so 1 goes in 1, has to go, and that's split. So this mapping does on the K0 level maps the 1 and 1, and that's the only thing it can do, and it has a kernel all the rest of it. Now K1 was 0, so K0 is trivial, the 0. This map can on K1 can only be the 0, 1. So classical and quantum, we do have the same induced maps. So it indicates we do the right thing, and indicates we should really recover the classical K groups, because we use the same our DAO, which has all the information about the cluing on the K theory level, does the same thing. So okay, now I start chasing 6-term exact sequences. The title was about spectral sequences, but this is a motivation. Now, one of the ways I can compute and prove that these are the K groups doesn't change is chasing 6-term exact sequence, 6-term exact sequence, but the spectral sequence It's a tool which orders all of them in one gadget. So let's do the elementary thing and see how it goes. But yeah, it's in this case it's still simple because, as I say, it's DAO have just trivial maps. We have these K1. If you look at K1, well, the compacts have no K1. Then we had by induction, we had no K1 in the low dimensional spheres. So 0, 0, K1 remains always 0. We are fine. Here we have this from the complex Z gets included. We have an exact sequence Z, the CB K+1 view, and we had the projection down on a CBK, which has ZK plus 1. So here you see that again it splits with these are 3 groups. So we get 1 copy more, and then we see, yeah, it works. We are fine. The interesting thing, oops, that's not what I want to do. But I say it's in the DAOs, and we can see in the 6-lemma sequence, we can't see the DAO, which has all the information. The reason is this DAO in this case is pretty trivial. Now, that's now I come really to, that was an example. So that's what I call a definition. That's where I say, okay, here's the answer of my moral question. So we have classical finite CB complex, we want to make it quantum. What we do is, okay, we obviously the poles we will replace by quantum poles. We have these restriction maps, so we have these quantum boundary spheres, and we close these boundary spheres to the previous skeleton of K-1. So and in the K skeletons obtained by gluing the boundary of the spheres to a K-1 skeleton. So in the dual picture, we have this map DAO. So in the moment, it just has to exist. Yeah, if I don't care, if I just want to have a quantum complex, so I don't care just if it exists. So I have a DAO, I have here a surjection, so I can define with this DAO the pullback, and I get a skeleton of higher dimension, xk by taking the low dimension, taking the K poles and gluing it over the boundary. So my aim is to preserve K theory. So I would like to have the K theory of the deformed complex is the same. Well, for the poles we did the poles, that was a requirement. Now, what does it mean? We want to have the same, we want to preserve K theory. Now, the K theory of the spheres is very simple. These are copies of Z, depending on even or odd, but we get only copies of Z. So to say that we do something analogous to the classical case is that these, well, by induction, I suppose that I have the same K theory for the lower skeleton already. And then I get these gammas give me some map from the K theory of the lower skeleton to copies of Z. And what I want to say that it's an analog is if the tau is the same map. So if these are Q or non-Q should be the same, it's lower dimension, should be the same groups. And I want to have the same morphisms. So it should modulo some permutation. So this map into ZL should be the same. Then I say, okay, that's really what I'm doing is the same thing, classical quantum. So what was that? Aha, now I would like to proceed by induction. I would say, I know that the K theory of K-1 is the same. I know that this map tau, which has all this information, how non-trivial we are gluing the things, gives on the level of K theory the same map. And the question is now, if I look at the K theory of the new complex of one dimension higher, can I guarantee that it's the same K theory? And here starts the trouble. It's actually the answer is we can't guarantee it. So here we have this exact sequence. Now, one of the ways these K theory of the corners are known classically. Now the question is if this exact sequence guarantees me that the K groups in the middle are the same, and we can't guarantee it. So I continue with chasing 6-term exact sequences. We will come in the end to the spectral sequence, and I hope it will convince you that it's a much better tool than chasing by induction exact sequences. Because now we face really the first problems. So we have these the projection from the higher dimension to a lower dimension. It's projective. It gives us exact sequence. I don't know if you if you look at this projection, so the kernel of this projection is exactly the kernel of the sigma k. So these are the insides of the balls, obviously. So we get the inside of the balls as the kernels of the projection maps. Now I have an exact sequence. I put it in the 6-term sequence of K theory. In the even case, we have these K1 of these spheres, 0, which is nice. So we can start here. And you see that our K1 of our newly constructed CW complex is the kernel of this index map. So this is supposed to be by induction the same group. These copies are the same classical, and these are these insides. These are classical and quantum the same. This is the same. So it's the kernel. And you see if the kernel, what I called it Q index map, because it's a quantum case, if the Q index map is the same as in the classical case, because these are supposed to be the same groups, then I can guarantee that K1 of the newly constructed complex is the same. But now if you look at the hierarchy, that's written here. So it's classical and quantum, it's the same, I'm fine. But if you look at K0, what I get is an exact sequence. So this we can suppose that the range is the same. So this is the same group, classical or quantum. This is the same group, classical or quantum. But if there is torsion, I cannot reconstruct. I have not enough information to tell what is a K0 group of my newly constructed complex. So in the case of torsion, I cannot guarantee that the Q version and the classical version are the same. But that finishes the whole induction process. In the production process, I said, I know that this K0 of the lower, it's the same. But now I can't. I simply don't know. And interestingly, here my cluing map is completely hidden. Yeah. Here in the 6-term sequence, we don't see the cluing map. Of course, we can have a good guess where it is. It is in the index map, which guarantees equality here. So we can do the same thing in the odd case, but the same thing happens, exactly the same thing. Now we have in 0 in the open disk, in the odd dimensional open disk, the K0 is 0. So if the Q exponential map is the same as in the classical map, if the K, so the previous K groups are the same, I know that the kernel of this exponential map is the K0 of my newly constructed CW complex. So having the same maps guarantees me K0 is fine. It's the same classical quantum. But again, I get for the K, now I get for the K1, these exact sequence. I have the same groups in the corners. So that's, I suppose that the exponential map, classical and quantum is the same. So this is the same group as in the classical. K1 is by induction the same group, but I can't say that I can't guarantee that K1 is the same because if there's torsion, I don't know how to recover from this exact sequence K1 of the newly constructed TW complex. And again, it seems that there's no Tau. Surely it's hidden in the exponential map, but my idea of taking induction doesn't work. So we need a better tool which avoids induction, and that are the spectral sequences. Here's another. It's another way to trace 6-term exact sequences, which is even more interesting because it keeps track of the generators. So actually, I had much more hope to solve the problem with Major-Vietoris. It's again a 6-term exact sequence, but in 6-term Major-Vietoris sequence, we have explicitly our Cluey maps. Yeah, we see how it appears and determines the K-theory. So if you go around here, in the even case we have here, it's something where it's just the triple K-theory. We have here copies of the balls, so that goes to the balls, go to the balls, that's split. So we can ignore these Z1 parts. We get a zero here. So what we see is that so the tau goes to 0, then K1. Where is it? Here. So that's 0. So we have an embedding, and it's exact. So K1 is determined by the kernel of tau. Very nice. That was the hope that it always will work, something like this. So the kernel tau does really determine K1. If I go to the K0, same extension problem. Now I have the range from tau. Now I know that's the same by assumption. It's the same groups. But since I don't know if K0 to K minus 1, if that has torsion, and here we have torsion, we don't know nothing about the middle. So the same thing happens. Induction fails. But here we see the only thing we need by the 5 lemma, so these are on the corners are the same groups. Now the only thing which I need is a map that goes either from the quantum case field group to the classical one, or from the classical to the quantum. Then the 5 lemma would give me the answer. But I need to construct these morphisms, and my hope was chasing these elements. Identifying the elements, I can define this homomorphism. But still, we didn't succeed. That's all. It's the honest answer. So in that case, it happens the same thing. I just take off these trivial elements, and then you see it's a 0. One after you have a 0. So it's an embedding, tau, delta, the kernel, perfectly, K0 in that case. And we have the same problem for K1. So we have the corners are the same groups, but if there's torsion, we cannot say it's the same. I could conclude it if I could say I construct this. One morphism would be enough. A morphism is enough, and then we could have an isomorphism. And the morphism I would like to define on elements, but I need to know where does these elements come from.
Sorry,
So yeah,
could you come back to the last page?
That one?
I don't understand what you mean by extension problem in the case of torsion.
No,
So the only problem is that you have this middle term presented as an extension.
Exactly. But you cannot say which
extension. This extension is given in terms of this map in this short exact sequence.
Yeah.
So what do you mean by the extension problem?
I cannot say what is that group.
What is what?
I know that maps exist. I would know much more explicit would not these maps. But that maps to know what these maps actually do, I would have to look at the generators, and I would have to look at relations.
So you mean that you don't have free generators?
What
This is your extension problem. You cannot construct in the middle
I
free generators, even if you have some free generators of this extreme terms, provided K1 is torsion.
yeah. I have a look at projective spaces. I have these generators, but I can map it, but I don't know if they satisfy certain relations. It's squared is 0. Yeah, okay, fine. But what does it mean exactly here? So it has two options. So the generator can, if it is a direct sum, if it's direct sum of these groups, that's one way. And then this generator can go to, if it's Z4, it could be to the square of one generator. And I cannot, this case, I tried it with that's why I included Meyer-Vietoris. I wanted to use Meyer-Vietoris to say that these maps have to be in the same, so if AZ maps to a generator or it maps to the square in the case of projective spaces. So I wanted to know if the generator of that maps into a generator. So I would know that that's the direct sum of Z2, Z2, or does it map in a square of a generator? And I couldn't decide it. I couldn't find a way to decide it where it maps.
Yeah. But the problem is that these generators are not uniquely determined.
Yeah. Yes. Yeah.
So the question from the scratch is imposed because you cannot get the structure of this abelian group in terms of free generators. If
Exactly.
You have
Exactly. Yeah. That
but
was
the
my
problem
problem.
is not with this extension. The
Yeah.
problem is that there are no free generators.
The tracing back on and finding the relations. Yeah, that was my problem. And I hope that if you look at Meyer-Vietoris, it's very interesting because Meyer-Vietoris, you know, is one subjective maps.
Yes.
So you can construct these new generators. You construct by Meyer-Vietoris only on one side, only on the inside of the board.
Correct.
Which is, then I said, or if that is only inside of the board, so that should allow me to conclude something about the relations. But then I looked at the projective spaces, and then there are some funny relations. So you have, if you take in, CP RP4, RP5, there was then this Meyer-Vietoris were two column vectors. And these two column vectors did really split into two generators. It was, things happened that I didn't expect. And so I gave up by tracing. But still, I hope that somehow in the spectral sequence, I can trace back the generators. Where do they come from? What are they doing? What are the relations? Yeah, it's, maybe I should give it up. Maybe it's just not possible. I don't know.
Probably not.
Yeah, most likely not.
And can you explain why induction doesn't work anymore? You can explain.
Yeah, because in the induction process, I said, I know that these groups, I know that these groups are the same as in the classical case. Okay. But here I cannot guarantee it. It's up to extension. So if you have Z2 here, Z2 here, you don't know if it's Z4 or Z2 times Z2. Yeah. So that stops the induction process, but spectral sequences, yeah, that's everything in one gadget. So I can say something about it. I cannot solve the extension problem, but I have information about the K-theory. And that's the nice thing about these spectral sequences. So that's actually what so all these things that the problems we face, that's what I say. It's spectral sequences don't need this induction process. In cases when there's no torsion, I get the K groups on the nose, and we haven't studied very well the higher differentials. I still have some hope that maybe the higher differentials give me more information. Maybe I too can complete these morphism. I can find a morphism. Maybe the relations that one satisfied have to be satisfied in the other. That would be enough. We did manage, or maybe we have to give it up. I don't know. But let's have a look at it. What spectral sequence tell us. And
Could you go back again? Sorry, when you write this problem, and when you say that the 5 lemma requires existence, and then you have these 2 dotted arrows.
Yeah, one is enough.
Why does the word require? I'm confused. Doesn't it mean?
Well, I need the morphism to apply it. If there's no morphism, I cannot apply the 5 lemma.
Okay, I got it. Okay, yes, okay, thanks.
It's very little. That's why I still fight with this problem, because it's very little. It's a bit like your correspondence theorem. If you have a correspondence theorem, if you can map it in, fine. Then you have the isomorphism. Yeah, but if this map, so in my hope was that in certain cases, when I have these balls from the doublets algebra, I know the generators. Those are so explicit generators. So I can say, okay, these generators, one of the generators from that group, if I map it down, it has to satisfy the same relation. Something like this would be enough, but, well, to be honest, last half year didn't even work on it. I haven't had time. But spectral sequence gives us a lot more information and skip also the introduction process. And that's just for Schochet's papers, it's all done. So there's nothing I have to do. I can just copy it from the paper, and we construct the spectral sequence by next couple. So we have these.
Sorry, Elmar. Could you discuss a little bit your previous page? Yes.
Yeah.
So
Previous page of the spectral sequence.
yes, for spectral sequence, yes. So first of all, you are assuming that you have some maps. You are doubting if there are way to define some middle map, but you take as granted that you have these maps. But these maps you wrote are fake maps in a sense. They're artificial isomorphism, abstract isomorphism of K groups.
Yeah.
Even on the level of this ZLN. Okay, so these are maps which are defined in terms of generators.
Yeah.
So the problem is not that this induction doesn't work. You are losing something from this induction. You are losing the identification of maps.
Yeah. But here, one of the nice, if you look at here.
So the answer to your problem is, why would you expect that you will get the positive answer if you forget about these maps?
No, we don't forget it.
You are taking some generators, you are identifying things abstractly. But
not
the
abstractly.
point is that so first of all, this induction works, but it doesn't work vertically, it works horizontally. You have a parallel computation for this quantized case in the same way as you obtained in the classical case. The problem is that you don't have these comparison maps, canonical comparison maps, but the inductive process is completely the same. Provided you are controlling the maps. If you forget about the maps, you have nothing. You have some random isomorphisms by picking generators. The problem is that if you have this inductive process, you have some uniqueness, but only up to modulo something. And So the only distinguished generator is the last one. So you have a triangular structure. So your transition maps between different choices of bases of these three groups forms a triangular matrix, which means that the only one generator which is canonical is the last one in your construction.
Yeah.
And you cannot lift them in a natural way. So in general, there is no hope to obtain identifications by identifying things via these highly non-unique choice of generators.
Well, I was hoping to keep track of the generators from the beginning. If you look at
no. The problem is that you cannot track them because only classes of them, modulo something, are determined uniquely. If you are starting lifting them, you are losing this uniqueness.
Naja, look, why I had so these balls don't participate. These are no generators. All these generators come from here. And if you look at my Viadors, I have here. My Viadors, do I have my Viadors? That's here. It's very explicit. So you take these elements can be identified. Let's have a look at, these elements, zetas, come from the generators of the balls. So I have the classical balls, I have the running balls, and I have the generators which I can identify. I call them bot generators. These generators I can identify. And my hope was, where's my Viadors? So these generators is very, very explicit. These maps, my Viadors maps are very explicit. So I wanted to keep track. Exactly what I wanted to do is step by step, keeping track where these generators come from. So I can say, where do they land here? And that's what I wanted to do. Here, I wanted to say, okay, the image of these elements I can compare. I have a classical and analog which I can compare. So the one that is constructed by my Viadors in the Q case is the same that I construct in the classical case. That was my hope.
Yeah, but the problem is that if you have these generators, they go to some elements which are not generators, possibly.
Exactly.
Or maybe some other generators are not.
Exactly.
Images of some canonical chosen. Like here.
And then my hope was, okay, if it's not a generator, so it has some relation. So it's a power, maybe it's a power of a generator. And these generators I wanted to identify again. There is a generator. So what my hope was, okay, that goes to some p squared. So what is a squared? Where does it come from? Can I identify it with a classical one? Yeah, you're right.
I understand the hope, but from my point of view, it's hopeless.
Reality. Well, reality has shown us you are probably more right than my hope. Your comment is absolutely correct because by experience, I must say you are pretty much right. But
okay, so to finish my comment here, so I agree that there is a problem with generators, especially if you expect three generators. But I cannot see the problem of this induction because this induction works exactly as in the classical case.
Okay,
there's one comment what I would make. So I didn't want to have a complete general result. I wanted to have these very special balls where I have this very special, what I call bot projection. I would say, okay, I know what the bot projection is. I know where it goes. So I wanted to say some way to detect that the relations, so some element does not go to a generator, but I can say, that's a bot projection and this is squared of that one. This one was my hope. So in a very explicit example, with my doublets operators, that was a hope, not a general theory.
Okay.
It's a very nice example. Yeah, I wanted to find balls with spot generators which allow to keep track of it. So it was less than it appears. It was not my attention to complete general result. So 50
Okay, Richard.
minutes.
Wait, Elmar. Richard wants to say
Can
something.
I?
Yes,
Elmar,
please, go ahead.
So I do have a problem. So these Q things are actually continuous deformations of the classical ones, right?
Yeah, yeah,
So there is a map in K, natural map in K theory from the classical to quantum.
yeah,
Mhm.
So these maps from classical to quantum are actually, they exist and they are natural. They have nothing to do with choices of generators.
yeah,
So you
yeah.
have a map between the two exact sequences, right?
That's true.
Not short exact sequences. You have a map between the 6-term exact sequences.
Yes, yes.
And that's enough.
Hopefully. You're sure? You say on the
Yes,
nose.
I'm quite sure, and that's what you are going to do, because what you have is actually you have these two spectral sequences, classical and quantum, and you have a map from classical to quantum.
Mhm.
And
Okay.
In the homogeneous case, but in
Yeah,
general, I'm not so sure.
what are you not sure? In
You
what?
are claiming that for general Q deformation, you have a map between K theories?
For continuous, yes.
Continues, yes. For
Continuous,
continuous,
continuous, yes, of course.
Okay, so I know only this result for homogeneous spaces.
It has nothing to do with kind of spaces.
Okay.
If you have a continuous field of C-star algebras, then for each point, you have map from K theory at this point to K theory in the neighborhood. Canonical map.
Yeah.
Well, just to show you,
So have a map.
to show you an example of the power of Q deformations, let me recall a beautiful theorem due to Makoto Yamashita, which is, if you want, a Q version of a famous Borsuk-Ulam theorem. And that's a very, very complicated argument, but it uses exactly the argument which Richard just used. He managed to, by a lot of very non-trivial gymnastics in KK theory, he managed to reduce the Borsuk-Ulam theorem, which was done for quantum spheres, okay? He managed to reduce it to the classical one, which we know is true, and then this is how he proved it. It is different from what we want to prove in our non-commutative Borsuk-Ulam type conjecture. It is different, but because we have a different setting. But this particular, on the nose Q deformation of spheres and maps between them gives a nice example of a quantum Borsuk-Ulam theorem, and was proved exactly by arguments a la Richard. I mean, by this continuous field of sister algebras argument.
Mm-hmm.
Just a comment.
Okay.
Okay, Elmar, you can go.
Yeah, thanks. Well, that's
But then,
both comments are correct.
So what's the situation now? So could you come back to this Meyer-Vietoris? If there is a map in the middle, yeah. So what is the problem now? No. You have this comparison of these exact sequences. No, the next slide. Probably next.
Five lemma.
Probably the next slide. Yes. No.
Lemma?
Yes. That
Yeah.
one. Yeah.
So we have this map.
So Richard said.
No, that's not a good sequence.
Hmm.
It should be a 5. It should be a 5 sequence to 5 sequence. You shouldn't just divide by. It should be a map between K theories. You have a sequence in K theories with 6-term exact sequence in K theory of one, and 6-term exact sequence in K theory of the other. And there's a map between these two sequences. Yeah, precisely.
Yeah.
That's what you are doing now, right?
Yeah.
That's what you are going to do.
Yeah.
Right?
I had the same worries as Tomasz, and I hope what you say is true. I wanted to see it in generators and I couldn't see it. So I thought it exactly as Tomasz thought it, that it will work. But continuous deformation is a good. It's yeah. It's a good hint to deform it continuously. This I didn't think about. Thanks for this comment. Well, that's all what I actually. That was what I wanted. At least an example where it works. That would be great. I will think about it. I need to think about it a bit slowly. I don't want to give answers now, which I.
Sure.
But it's a very nice comment, and it makes me hope to succeed what we wanted to do. But I have to revise it. I don't want to make mistakes. Now, the title was about spectral sequences.
Yes.
And that's now to finish the.
You're beginning of that. Now you're finally beginning.
Yeah. 10 minutes. Well,
yes.
The thing is, in any way, it's a motivation. This is a nice tool. Now, everything is in Schochet's paper, so we just can copy and paste it, and it's finite. So we have a very good situation. Now, we constructed the spectral sequence by an exact couple, and here you see this phasing fixed-term exact sequence. These, we have this inclusion map. So the ideals we include, then we project to the quotient, and here we have the boundary map. So we get in K1, you can get one higher, one lower, have it by Bott periods, it doesn't matter too much, and then you go around and around and around. So that gives you, so now here, the first page we define as the K theory of the quotient. And the differential is we skip this injection. So we go with a boundary map, and here we go to immediately to the quotient. That gives us the first page and a very explicit description of D1. Now in the second page we replace these E1 page by the homology of E1, kernel by range. And we still have this boundary map, we still have these injections, we still have the quotients, but now we have to take a bit more careful. So we replace here in the corner by the image. So under I, and apply again this injection. But if we want the quotient now on an image is taking the quotient of the original element, and that will be in the kernel of D1 by exactness. So we have an element in the homology, and the boundary map is taking the boundary map, and then applying I gives us a 0. So we're still in an exact couple. So from one exact couple, we replace this page by homology, construct another exact couple, and then we go on by induction. And the important thing is, since we have these inclusions, but we after the inclusion, but we act on the element that comes from the inclusion. So we get our differentials map now. I choose the way that is dual to homology. So homology is exact spectral sequence for L to the right and L minus 1 up, and I go L times to the left and L minus 1 down. That's just convention. So here I tried to write everything in one slide. So we have these exact couples by induction. Now the D1s go just one to the left, nothing to down. So then I replace it by homology of the D1s. And the D2 go now, here we see 2 to the left, 1 down. And so it goes, the DL will go L to the left, L minus 1 down. And these are finite spectral sequences. So the differential N plus 1 comes from a 0, goes N plus 1 left and down. So the 0 hits 1. So these elements come all these elements are hit from a 0, and all these elements that go out, here's is an example. So it goes n plus 1 to the left, down goes to 0. There, the homology first stationary, so all from n plus 1, all these pages are just the same. And that's our easy, nice situation, because it converges after n plus 1 step to the infinity page. And the question is, what does it tell us? Yeah, the infinity page. So we want to have, so the K0 is hidden if we look at the diagonals. And K1 is if you look, maybe we can see it here still. No, there's no, okay, it's hidden in the diagonals. It does not give K-theory of our distal algebra. It gives the K-theory of the associated graded object. So if we sum up all these K0 groups, what we get is a corresponding quotient. So here it's the extension problem is here. It doesn't disappear, but since there's no instruction step, well, we get an information, we do get information about the K0 groups, the associated graded object of the filtration. And K1 just the same. So no induction step, a lot more information, and we get information of our distal algebra, which is constructed by a finite W complex. So where does the filtration come? Well, it's exactly as in the classical case. We have these projections down to here from from the K skeleton, we have a projection to the K-1 skeleton. And the filtration is there's corresponding ideals. So the first from the CN, our finite construction, the first projection to the N-1 complex, the kernel is A0, and it's on the nose we see that's the open balls, open end balls. But then we go down with these projections. These are not balls anymore. These are just these are basically we can see it in the classical case. These are the zero function if we take out the n minus k minus 1 from the xn skeleton, we take out the n minus k skeleton, and then these are the zero functions. So that goes from 0. The last one is our algebra of interest. And the nice thing is, if you look at the quotients are simple. So the quotient gives us just the open balls. And the open balls have easy K groups. These are these copies of Z. So we start with our first page has only copies of Z and the D1, which is related to our Dow K. So yeah, that's one of these examples. So these are the just K0. That is algorithms K0, K1, K0, K1. These are all these copies of the numbers of balls we have. Then these are the zeros. So K0 of an open odd-dimensional ball is 0. K1 of an even-dimensional open disk is 0. So we get zeros here, and then it repeats, but it's a strip. So it's a finite strip. That's why it converges so easily. So, and here's you have little time. This is my example where you see really it's a beautiful tool for the quantum complex spaces. Well, we have to compute the D1s, which relates to our fluid maps. But here we see that we had only skeletons of even dimensions, so dimensions are 0. So D1 can't do anything else than in the classical in the quantum case. Yeah, all these D1s are 0. So we can replace E1 by the E2 page. Homology looks the same. That's the infinity page. And now we can read off. We have no extension problem because we have only copies of Z. We just count the numbers of Z. It starts from a 0 dimension, then to the one projector space, so the 0 dimension, 2 dimension, all even dimension have copy of Z, makes Z n plus 1. and the K1 groups are all zeros. So once it knows K0, we look at the spectral sequence and can read off the K groups. So that's where the power of the spectral sequences are. So now it's the question is, now comes the technical details. I was saying we need to keep track of this. So we do the computations. I don't have the time. There's a lot of boundary math extension, making sure it's in the right ideal. So these are complications, all the calculations, which I have no time. So it looks like, so D1 of U, what I have to do is extend it to the, here's D1 we see. The first thing is a boundary map. So we have to take our element and extend it actually to AK plus 1, this is W. Then we squeeze it in a projection. So if you project down, then in the K0 theory, so U is a unitary matrix. In the K0 of the AK, have to project down, so you have to take mod AK minus 1, and these V's are part of the construction. So these V's we can see here. These V's were lifts of the maps. So from U comes from the open bowels, but I can compactify it by 1. I can take the 1 of the n minus k minus 1, so it automatically defines an element you tilde on the n minus k minus 1 skeleton, and then I take these project down, so it finds me a K-theory class in mis thetas, which I easily can compare classical and quantum case. That's where the so V is a lift to the balls, and it's squeezing in to some projection 0. This is the boundary map in K-theory quotient. We get the squeeze as taking from here this element which was pushed down by the Tau. So takes a boundary map. The boundary map goes to the kernel of the K of the kernel, which are the open spheres. So if we ignore it, because that is it's an easy isomorphism which identifies generators and generators. We can stop here. So the D1 is in modulo some trivial homomorphism is exactly the induced map by Tau and n minus k. So that makes it very close. So here's a classical in E1 quantum, it's really the same. And now with Richard's remark that we should consider continuous deformation, so this might gives the result. So yeah, I have something more, but I need to stop here because time is over. So thank you for your attention, and thank you for your good remarks.
Muchas gracias. Yeah, after this presentation, I hope at least native speakers agree with me that one really need to have balls to speak about quantum CW complexes. Okay, questions? Claude, you are the guest of honor, so any questions? You are muted.
Okay, let's try it now.
Yeah.
I don't understand much of anything about the quantum situation, but this is in the direction of the Richard said that. So let me say it in terms of these ascending sequence of ideals. If you have an ascending sequence ideals A1 to A2 to A3, A4, and so forth, and suppose you have another one B1, B2, B3, and so forth, and you have a map from one sequence to the other sequence. And that map induces an isomorphism when you look at the K-theory of AI over AI minus 1 in every case. So you're mapping from the K-theory of the quotient of AI minus 1 over the quotient of the K-theory of BI over BI minus 1. If that map is an isomorphism for all in all cases, then there's something called the spectral sequence comparison theorem, which says the whole spectral sequences are the same. So you don't have, this is along the line of what Richard was saying about the Meyer-Viator sequence, but it's stronger. And it's a classical result about spectral sequence. It doesn't really have anything to do with K-theory particularly. But that might be a useful tool for you to use.
With internet, can someone?
Elmar, your internet is breaking. You have to, your internet is breaking, Elmar.
I couldn't. It was broken.
Yeah, but it's your internet, I'm afraid. You, for the last few minutes, your internet is refusing to cooperate.
Do you want me to say it again?
Elmar, are you frozen completely? Because
Yeah.
Claude asked you a question. Do you want him to repeat his sentence, what he said? No, I mean, it's completely frozen. Okay.
Yeah.
Elmar, you are vanishing. So do you want Claude to repeat what he said, or?
Yeah. I didn't understand anything. I was frozen.
Okay,
I didn't know who was frozen.
Okay, I'll
You
try
were
again.
frozen. Okay, Claude will do it again. Thank you.
I'll try again.
Yeah.
Suppose you have the setup with A being the ascending sequence of ideals, the AIs, and suppose you have another one with the BIs, just call them A and B. And suppose you have a map of C-star algebras from one ascending sequence to the other ascending sequence. Then that map induces maps on K-theory. And if you take, say, AN divided by AN minus 1, and it will go to BN over BN minus 1. And if those maps are isomorphisms on the K-theory level, then the spectral sequences are isomorphic. And that might be a tool that it's called the spectral sequence comparison theorem. And it might be useful to you in some of these calculations.
Yeah.
You understand me? I was frozen again. Can you
Yes, sorry,
understand
we will
me?
not repeat it the third time. Okay,
Not the word.
You will be able to watch it on YouTube. So, Claude, thank you so much. This was very interesting. Anybody?
May I comment on
Yes,
this?
go ahead.
There is a problem with the application of these maps inducing isomorphisms on K-theory, because in the case of Q quantization, such maps do not exist.
Oh, okay.
Okay.
There are KK elements which are invertible instead.
Yeah, KK elements, but not maps.
Yeah.
So no, there are no star homomorphisms, but there are KK elements.
Yeah.
So it's in KK category instead of star homomorphisms.
Yes.
Same argument, same statement as Claude is saying.
Yeah. That's my feeling. Yes. Okay, anybody else would like to weigh in? Anybody from here? No. Adam, you usually ask a question.
No, I don't have any. Thank you.
Okay. So anybody else from Zoom would like to weigh in? Okay. If not, let us thank Elmar again. Thank you so much.
Thanks, Elmar.
This is a very exciting talk. Thank
It's
you
good
for-
seeing you.
Yeah. Thank you both for coming. Let me now stop recording, but please don't go away.